Hello to everybody. We are starting our seminar of the IAU Commission, the local universe. And today we have a presenter, Cecilia Mateu from Uruguay, and she will tell us about the current inventory of Milky Way stellar streams. This subject is very important nowadays, so we are happy for your presentation. You can start.
Thank you, Yasina, and thank you for encouraging me to participate in the series of seminars, and thank you to the organizers for keeping these virtual seminars. They're super interesting and extremely useful. So it's great that you've kept this initiative after the pandemic. So yes, as Yasina already said, I'm going to be talking about the current status of the Milky Way stellar streams field a little bit because of a paper that I recently published that I'm going to be talking to you about, compiling all the information on these stellar streams and making it available to the public. So I want to start with let me move this over here. I want to start with the very basic, with the actual definition of a stellar stream, just so that we're all on the same page. And a stellar stream, or a tidal stream, is the structure that is formed when we have a dwarf galaxy or a globular cluster that is orbiting a more massive host, and it has its stars torn out of it, and dark matter as well, by the tidal forces that the more massive host it's exerting in it. So in this animation that I'm showing you here, you're seeing to the right what's happening to the stars, to the left what's happening to the dark matter and the stars, and you see how stars start escaping the progenitor, the dwarf galaxy or the globular cluster, and they start getting spread out because of these of the tidal forces. So these have been observed both in our Milky Way and in external galaxies. Here are a couple of examples of a very impressive, amazing survey of tidal streams in external galaxies that David Martinez Delgado and collaborators have been conducting for many years now. And well, the point about stellar streams is that stars are phase mixed, and they produce these very interesting structures that will eventually phase mix in and become part of the smooth components of our galaxy, mainly of the halo. But because these dynamical times in the halo are very long, in this part of the galaxy and in other galaxies is where stellar streams are longer lived, and we can actually see them lasting for several millions of years and even a few giga-years. So stellar halos are where most of the streams are found. They're the ideal places to search for tidal streams because this is where they're long-lived, but also because the contrast is more favorable there to find them. So it's observationally easier to find them. So I showed you this couple of examples so that you have a picture in mind in case you didn't already. And we're going to delve in now into what is the status here in the Milky Way. So this animation that I'm showing you here is the state of knowledge of tidal streams circa 2010, more or less. And here you can see a representation of our Milky Way galaxy. Here is the position of the sun. And the very first tidal stream that was found in our Milky Way, which is caused by the Sagittarius dwarf. So this is the Sagittarius tidal stream, which is a field of research in itself. These are different multiple wraps of the Sagittarius stream. Here is the monoceros stream, a structure that we now know is associated actually to the disk. And then there are other structures like the Virgo overdensity here that is not formally a stream, but it's more something like a cloud. So this is relatively in the beginnings, so mid-2000s. And this is basically the picture that we have right now. Close to 100 streams have been identified in our galaxy, and it's getting more challenging to keep track of the streams we know of, where they are, and what information is available for them. So, so this is what we're going to be focusing on now, but what are the actual questions that motivate our interest, our scientific interest in stellar streams? And because I come from a background on stellar populations, the way I like to think about this is that stellar streams are to dynamics what stellar clusters are to stellar populations. So relatively simple systems of stars that have a common origin, and it's that set of common traits the stars share that allow us to pick them out better against the background and understand them more easily than to rewind evolutionary processes that would be very hard to understand in the field. So in the example of, in the case of clusters, stars can be thought of as having the same age, the same chemical composition, they lie at the same distance. So when you overplot them against the galactic background, they really stand out in a color magnitude diagram, for example, as I'm showing here. In the case of streams, this would happen in a more of a dynamical plot in which we're focusing on conserved quantities, for example, the total energy or a component of the angular momentum, where the smooth galactic background is represented by the gray stars here, and streams stand out as overdensities, very localized overdensities in this plane, because they retain memory of the energy and the angular momentum that they had when they fell in together. So, like I said, these common properties, these things that are conserved and that are similar to stars, for stars within the same stream, are useful to find them against the background, the much more populous background. And they can also, modeling them can also be used to infer properties about their own origin and about the galaxy host that produced the stream, in this case, the Milky Way itself. So pushing the analogy a bit further, the same way that stars in a cluster delineate an isochrone, as we know and we just saw in a color magnitude diagram, stars in a stellar stream approximately delineate an orbit. So in the plot that I'm showing you here, you have the stellar stream of the Pal 5 cluster, the second one found. It's the poster child of stellar streams. You have the cluster here, and the ISO contours represent stellar density along the stream. And the different dashed and dotted lines are different models of the orbit of the cluster. So you can see that the stars along the stream are acting as a trail of breadcrumbs that are telling us where the orbit is. So where the cluster has been and where it's going to be in the leading and the tailing, in the trailing tails. So fitting orbits of stars in stellar streams can be used to infer the potential in which the stream is created, in this case, the Milky Way potential, and it can be used to understand its shape, its mass, its enclosed mass within the orbit of the stellar stream, and also the total mass of the Milky Way. And then modeling substructure along the stream, you can see here that the density, there are some slight density variations along the Pal 5 stream, but this is more starkly seen in the GD1 stream, shown here below, where you can see there are very clear density variations and even gaps on the stream. These are absolutely real statistical significant gaps. They were found in this case by Iran Perdisuilan and Anna Bonazza in 2018 with Gaia DR2. And studying what the substructure is along the stream, the presence of things like spurs, also found here in GD1, or even a cocoon, as Mounhan et al. have claimed there is in this particular stream, can tell us about what the initial configuration of the stream progenitor was, in this case, the globular cluster that produced the GD1 or other stream, but also about properties of possible perturbers, as in this case, because these authors have proposed that these are the long-sought gaps that very cold stellar streams might have when impacted upon by dark matter subhalos. So this is the most clear case in which this has been detected, but you can imagine that by trying to observe this in many different streams, then well, all the possible degeneracies that are involved in this process can be alleviated, if not broken, and then inference on all of these things can be made to try and understand what the mass distribution of dark matter subhalos that don't have any stars or very few would be, and to understand what the initial configuration of the progenitors of the streams were. So fitting not only individual streams is useful, but now trying to fit and use ensembles, groups of streams for inference is also a very powerful tool. But then there's also the more straightforward goal to be pursued with stellar streams, and it's that they're quite obviously a remnant of the accretion process. So one would hope to be able to reconstruct the accretion history of our galaxy, something that schematically would look like the plot here to the right. This is just a cartoon of mass as a function of accretion, look back time, or inflow redshift, to try and figure out what the big building blocks were that were accreted and what mass they had and when they were accreted to form what is now the galaxy. Of course, the thing is, it's not so straightforward because stellar streams are part of the fossil record, not all of it. So they're not the entire accretion history. And they're probing this sort of Goldilocks zone in terms of accretion look-back time, because they can't be either too old or too young, or to recently accreted events that produce tidal streams. So when, presumably when the event is very old, it was accreted in a very early stage, it's now become either fully or almost fully phase mixed. So it's too disrupted to be recognized as a stream. So this would be a case like the Gaia-Enceladus merger that we now know in the Milky Way, or many of the other early mergers like Sequoia and so on. And then the very recent infalls, well, haven't had really any time to be disrupted at all by the tidal forces. So if they're just things are being accreted now, they're simply not going to be affected by the tidal forces, and streams have not had time to develop yet. So stellar streams are the ones that we observe are sort of in between in this accretion look-back time plot. And then there's also the issue of the mass. And that's because, well, if a stellar stream is produced by a dwarf galaxy, then it probably had, let's say, sufficiently significant mass to be a relevant block in this plot. But what we know right now is that of the close to 100 stellar streams that we know in the Milky Way, the vast majority, and when I say the vast majority, 90 out of those, almost 100, are very cold streams that presumably had globular cluster progenitors. So in terms of their mass, you'd think that they would contribute negligibly to this plot. But here the trick is to think not of the streams individually, but as groups. So as several authors have shown, Anna Bonazza, for example, or Conrad Bergson in an entirely different study, have argued that it's useful to try and locate groups of stellar streams that fell together, ensembles of stellar streams that might have fallen together, so that they can be used in the same way that the systems of globular clusters are tracers of the masses of the galaxies they inhabit. So if you have a galaxy and a system of globular clusters, the number and the mass in globular clusters of a given galaxy is a very good tracer of the mass of its host. So we could be using stellar streams in that same way, preferably in conjunction with surviving globular clusters to identify groups that may be that may have been accreted together, that may be signaling some of these major building blocks in the accretion history. So again, studying ensembles of streams may be very informative in this attempt to reconstruct the accretion history of our galaxy. So in trying to do that, the first step is knowing what we've got and trying to get it organized and see what information is available and whether that's enough to address all these scientific questions that we're interested in, and also to see what the holes are that need to be filled. So what is the current status in the Milky Way? This is another view of the plot that I showed you before, but now in celestial coordinates. This is in galactic coordinates, so the galactic disk is here in the equator of this plot. And if you're interested in stellar streams, you are probably looking for your favorite stream in this table. And a couple that I already mentioned are the Sagittarius stream, which is this big purple line. This is the Orphan stream, and this is Pole 5 here. And then you can look for your favorite in the table here. So you can see that this is all very tangled up. This field, like I already hinted at with the animation from the late 2000s, has been growing very rapidly and very organically. This is a timeline of the discovery of streams from the discovery of Sagittarius in the mid-90s to the burst of streams found by the SDSS. And then you can see here the burst that came with the release of the first data release of Gaia that had proper motion information, which was DR2, which has more than tripled the number of streams that we knew in the last 5 years only. So this has all grown very rapidly, and keeping track of what streams we know, where they are, and whether you have something new in a given patch of the sky is becoming more challenging, let's say. So the information is scattered across the literature, and there is no common standard or convention for reporting when a new stream is found. So you can see the whole spectrum from tables of actual individual star members being published, or coordinates of endpoints, or knots, or a polynomial equation that describes where the track of the stream is, or just points in a figure telling you to squint and try and see where the tidal stream is in a star counts map. So it's very varied, and this is what motivated making this inventory of galstreams that I'm going to be showing you here, to try and homogenize all the information, find out what information is missing and for what streams, so that we can redirect follow-up efforts where they're needed. So this plot here summarizes some of the information that's in the library, and you can see here that 2/3 of the stream, this is very conveniently because it's 100, this number is also basically the number of streams that have a given property shown here. So almost 2/3 of the streams in the library have proper motion information, which is very surprising, thanks to Gaia. And also, somewhat surprisingly, I would say, only half have information of the distance along the stream. So about 45 streams have only a mean distance, or even in some cases an assumed distance. So measuring the distance to a stream and along it, it's critical for any dynamical inference that you want to make. So this is one of the things that that particularly I learned by making this compilation, and it's one of the efforts that we're making in trying to fill this gap of actual distance measurements along the stream. So along the stream for all these streams that don't have it. So having a compilation like this was critical to be able to try to automate these efforts with so many data that we have right now. It's absolutely critical to have a homogeneous starting point where everything is in the same format, and to try and conduct automated member searches using all the breadth of the very deep photometric information that's available now in conjunction with Gaia. And also for the very practical and simple reason that if you find something that you think is new in an area of the sky, well, to be able to claim that it's new, it would be good to compare against all the known structures and make sure that we're not really rediscovering things that have been known for some time. So what information is available in the library in galstreams? This is a package. It's a Python package that's publicly available on GitHub. It's the galstreams repository. And the information that's in the library is the celestial distance, proper motion, and rate of velocity tracks for the 95 unique different stellar streams, compiled in 127 different tracks, because, well, these two numbers are not the same because there are multiple tracks for several streams that have been either found or observed by different methods and reported in different works in the literature. So the key word here is track. This is not a list of members. So what is a track? And here the plot that you have here below shows you that a track is simply an array of points of celestial coordinates that tells you where the stream goes. In this case, in the first panel, this is galactic latitude against longitude. So it's just a coordinate against an angle. And this just tells you where the stream is in the sky. This tells you where how this distance changes with a long stream coordinate, and in this case, the longitude, and these are the proper motions. Of course, what information is available, like I said before, depends, because not all the streams have, for example, proper motions. Not all the streams have distance along the distance gradient along the stream. So because this is all built upon AstroPy skycord objects, it inherits all the amazing functionality of AstroPy for coordinate transformations. So there are a lot of other subproducts provided with each of the tracks, like the poles that I'm going to be talking about, and also streams coordinate frames, in which each stream has its own coordinate frame defined such that the stream's mean plane coincides with latitude 0. This is usually referred to as phi1, phi2 coordinates. So the stream is usually as close as possible to phi2, 0. And you can see this is the same stream, how it looks like in this new rotated coordinate frame. And this is provided automatically for all of the streams. So this is just a very brief example of what the tracks look like for some other streams in the library. This is PAL5 again. This is where the cluster is, and these are 3 different tracks from the literature. So you see them here in the sky, here in distance, and then in proper motions. So for example, this latest extension of the PAL5 leading tail is observed in the sky, and this is the distance the authors report, but that has no proper motion information. So here you have the orphan Chenab stream, in which the orphan stream, which had been found in the early 2000s in in the northern part in SDSS by Carl Grillmeyer is now linked to what was found as the Chenab stream in the DES survey. And this is now the most comprehensive track, the light blue one, for the whole orphan stream, which tracks it all across the sky, all the way from the north to the south, and connects these previously thought to be two different streams or tracks. So then you can also check things like consistency of streams attributed to the same globular cluster, like in this case, M68. There's the M68 stream found by Palau and Miralda Escudé in 2019. That's this P19 yellow track here. And the Fjorm stream from Iwate, you can clearly see that these are the two in all the same, these two are the same stream in all these coordinates. But then the stream that was attributed to M68 in this Streamfinder paper by Iwate et al. Is entirely, it joins up well with the cluster, but it has a completely different proper motion in both mu-phi1 and mu-phi2. So this is probably a different stream. This is just an example of things that are interesting for us to look at and try to connect, well, things that are disparate in the sky or that are in the same part of the sky, but that are actually belonging to entirely separate structures. So, so what I've told you about now is what is in galstreams, and I just don't want to go with showing this slide of what is not in galstreams. And what is not in galstreams is the all-coveted, long-desired table, master table of all the stars with individual coordinates of stars that belong to each of the streams. This is something that does not exist. It has been published by many authors that have found streams, and you can see in all the summary tables in galstreams for which streams that is available and for which streams it's not. But it's roughly, let's say, something like a third of the streams that have individual star numbers published. Most of them have just the tracks, and that's what's in the library. The idea is that the library is the first step towards building this database, this atlas, which is a very big community effort that we're making that I'll mention in passing in my conclusion slide. So no individual stars in galstreams. Tracks, that's the information that's there. Mention a couple more things that we can look into with that information that is interesting. One of the things that we can compute are orbital pole tracks, and the idea of the motivation for this is that when you have a stellar stream that is formed, that is produced in a perfectly spherical potential, the stream, however complicated it might be, will be perfectly planar, and that plane will contain the galactic center if it was produced in a perfectly spherical potential. So if you look at the normal vectors of the different sections of the streams, or the normal vectors or poles, those poles are going to be parallel to the angular momentum of a given section of the stream, and every section of the stream will have the same pole. So it will produce in these pole count maps a very localized signature. As soon as you perturb the potential and it's no longer spherical, maybe it's squashed a bit, then this the orbital planes precess, and then the pole becomes, it ceases to be localized and it becomes a track because the orbital plane is changing along the stream. So it produces something more complicated like this. These are examples from the Aquarius simulations from work we did with Gaia mock catalogs and trying to automate stream searches in 2017, back before Gaia DR3. So having celestial tracks and distances mean that we can now compute the orbital poles along the track. So in little sections along the stream to see whether or not the poles change, and if they do, well, to see how. And you can see here an example of what happens for the pole track in the orphan stream. So this is the northern part of the orphan stream, and this is the southern part. And you can see that this is clearly not a point, and there has been something going on. And these, the green and purple lines, are what you would expect the precession of the orbital pole for orphan to be if the potential were just simply axisymmetric, so if it had some flattening. And you can see that the track, the precession track, matches just a little bit of orphan, and then something weird is going on. So, and more about this in a second. So the idea is that by looking at the pole tracks, we're looking at the direction of the angular momentum. So 2 out of 3 components of the angular momentum vector. But we're doing this without needing any velocity information, which is when now we have proper motions from Gaia, but radial velocity is always very difficult to get, and we only have that for about 1/10 of the streams in that we know of. So that's very expensive. So tracking a stream's pole is interesting, and it's very convenient, and it can be done for the whole galaxy. So once we do that, we can look now at preferential alignments of orbital poles, the same way that it's been done by different authors for the dwarf galaxy satellites of the Milky Way and globular clusters. And for example, Marcel Pawlowski have found that and argued that the orbital poles of dwarfs and clusters in the Milky Way cluster in a structure called the VPOS, the vast polar structure. And so the poles are preferentially aligned in this area here. So we can revisit and see whether this happens for the streams as well. They did this in about 2012, so there were only just about a dozen streams in that time. And they were arguing that there might be some clustering. This was revisited by Riley and Lyrae using an earlier version of the first version of galstreams, the 2018 one. And they did this for all the streams in the library in 2020. And they found that the streams poles do not preferentially align with the VPOS. So each dot that you see here corresponds to the mean orbital pole of a stellar stream in the library. And this is where the VPOS is. But because I've just told you that the mean doesn't represent the full information, we can now do this more exhaustively and just compute the whole pole track and not just the mean. So we can do that with the latest version of the library. And here, each gray line corresponds to a pole track of a given stream. So you can see first that they're not well localized. That's the first thing. Some are, but most are not. And you can see that there is absolutely no clustering around the VPOS. If anything, there's like an avoidance zone. So there's definitely no clustering around the VPOS. This is not an observational bias. It's easier to detect poles here because to detect streams with poles in this area, because these correspond to polar streams, so streams that are almost perpendicular to the galactic disk. So this is definitely not an observational bias. So this is one of the things that we're looking into to see whether there are actual clusterings aside of the VPOS that might point towards, groups and ensembles of streams, like I mentioned before, that might have fallen together and so on. So this is one of the things that we are interested in by looking at the poles. And the other thing that I mentioned was that precession wasn't enough to explain the pole track for the orphan stream. And when you look at the proper motions of the orphan stream, in particular with the Lyrae stars, Sergei Kopasov found that when you look at the orphan stream and the direction of the proper motion vector, because we started by saying that stars along a stream more or less delineate an orbit, you would expect the proper motion vector to lie along the stream, to be the stream's tangent. And you see that in the northern part, that is mostly the case, but in the southern is manifestly not. In fact, the proper motions are pointing almost perpendicular to the stream. So they're very misaligned with where the stream track is. And this was incredible. This was very surprising. And later, this is a set of two papers by the same collaboration. Denny Circle and collaborators found that when you quantify this, as I just said, comparing the stream tangent, which is the red line, and the proper motion ratios, which are the points, these two things should coincide if there have been no perturbations. So you can see here that that misalignment is really significant, even if you account for the errors in the proper motions. And what Denny Circle proposed and has been quite accepted is that that misalignment is due to recent interaction of the stream with the LMC. The southern part of the stream received a kick a couple, like 100 million years ago by the LMC, and that's why the proper motions are pointing in an entirely different direction. So the stream that we see now is no longer the orbit of the orphan stream, at least not in the south. This has been observed in other stellar streams by Noraship et al. And for example, in the Indus stream, in Jalen, and this one, Turambura, and these are all streams that show some misalignment. Not all of them do. All of these are in the south, and the size of the perturbation is consistent with it having been caused by the LMC. We can now do this same exercise for all the streams in galstreams that have proper motion tracks, and we can now map proper motion misalignments in the sky. So here, each one of these colored dots has a color scale that is proportional to how misaligned the proper motion and the tangent track is in degrees. So the darker means it's worse, so there's more misalignment. This line here corresponds to orphan, so this is the part that you already know that we just saw. This is the part that was affected by the LMC. These are the DES streams that I just mentioned from Ship et al. But there are some cases in the north where there's very clear signs of misalignment as well. And it may have been because, of course, this was the perturbation happened some time ago. It may have also been caused by the LMC and SMC. These have not been explored. We have to look into that. And well, there's also the question of whether Sagittarius, which is also reasonably massive, has induced similar perturbations in other streams. So this is something to look into now, but with many more streams that are available in the library. And the very last thing that I want to show, I think I'm okay with time, right, is that because we can't go without mentioning our Lyrae stars, in trying to fill this holes of information missing from the stellar streams, we're doing an automated search of our Lyrae stars in the different streams. And we started this with the easy case of PAL5 in 2019 with Adrian Persuelan. And we found the Lyraes associated to the stream with that probabilistic method and reported the first proper motion track for the stream and distance along the stream as well. And when we were looking at the Lyrae stars by type along the stream, we found something that was very confounding. And here we're plotting the Lyrae with colors as a function of their type. So the purple ones are the first overtone, the AB pulsators, and the yellow ones are the first overtone. So wait, I think I said the same thing twice. The AB are the fundamental mode pulsators, and the yellow ones are the first overtone. So the two types of Lyrae stars. In the cluster, PAL5 is very rich in type C Lyrae. Almost all the Lyrae in the cluster within the core radii are type C, and there's only two type AB. In the tails, it's exactly the opposite. All the ABs are in the tails, and there's only a couple of type C RLR in the tails. So it seems like they're segregated by type, which makes no sense because the masses, the differences in the masses of these two types of stars is in the tens of solar masses. So it's too small to be able to explain this. This is something that we don't know if it happens in any other stream. We don't know if this is just an effect of all five. This is definitely not a completeness effect. We are sure of that. We know and have this well understood. So one of the things that we are doing, because we are interested in producing distance tracks, but also in looking into the RLR population, is conducting an automated search for RLR members on all the galstreams tracks. And this is part of a student of mine's master's thesis. Bruno is working on that. So ask me more on that if you'd like to hear. So just to wrap up so that we have enough time for discussion. There's a breadth of information available now for stellar streams. Now is the time for ensemble studies of stellar streams. But to be able to do that, it would be a pity not to fill in some very sizable gaps in the data that we have for many of the streams, in particular, missing distance, detailed distance information for almost half of the streams. This effort is something that goes way beyond one single research group. This is something that we started at the Streams 22 workshop in Pasadena late last November. And our goal is to produce a community atlas of tidal streams. So the acronym of the collaboration is the CATS collaboration. And we're working on deciding on and applying uniform procedures to probabilistically identify members for all the known stellar streams. And because this is a highly curated task and we're trying to automate it, we're starting with 5 streams that are prototypical of different issues and problems and things that are hard to find. And well, this is an effort that if you'd like to join, please reach out, because we are going to make this available for the community as we, not just the atlas, but the actual pipeline and the software itself. So our goal is to obtain that all coveted list of stellar members to all the known tidal streams. So let me just wrap up by saying that stellar streams are amazing tools to learn about the Milky Way and galaxy formation at dwarf galaxy scales. And if you find something new, tell me about it so that I can keep the library up to date. And I'll leave you with my thanks and with a small advertisement for the Latin American Regional IAU meeting that will be held in Montevideo in the spring, so last week of November, and registration is open until July 31st. So thanks.
Thank you very much. Indeed, so interesting, and you made very valuable work collecting all the information about streams. I'm curious, do you plan also to collect information on chemical composition investigations in different streams?
Okay, this is something I've been asked, and so I had initially not, but yes, for the CATS collaboration, one of the things that is becoming clear that is useful is to have a summary of the stellar population of the streams. So the age, the luminosity, and the metallicity. So yeah, the updated answer is yes, I think so. Yes. And I think that's not going to take as long, because we're probably going to crowdsource it between several of us, because it's much harder to collate that information, that the coordinates, because it's usually buried deeper in the text of the streams. of the papers, but I think it's inevitable that we do, that I do.
So I think that maybe easiest way is just to collect references to abundance investigations. Maybe first, at least such step could be made.
Yes, so I didn't show this, but I had it just in case. This is the list of references for all the information that's already in the library. And in many of these papers, there's already that data. It's just that I didn't collect it when I was preparing this version.
Okay,
Yes.
very good. Do participants of the seminar have questions? Please ask.
Hello.
Hello.
Yeah, so I had a doubt. You said that the discrepancy or the gaps in the streams was because of the dark matter subhalos, but they could be caused by giant molecular clouds or Milky Way bar also. So how do we differentiate which gaps are caused by whom?
Yes. So in this case, the case I showed, GD1, this is the one where people, they propose that's the origin. Of course, as you say, there are many other effects, but GD1's orbit doesn't come close to the disk. So for example, in PAL5, the effects of the bar and the interaction with the disk are highly complicated, and they're likely, and they have been studied. For example, Sarah Pearson has several studies trying to explain why the leading tail is so much shorter, and many people think that that's due to chaos induced by interactions with the bar. So that depends very specifically on the individual stream, whether or not its orbit is such that these effects might be important. So the good thing about GD1 is that all of these things are thought not to have played a role. So that's why in this case, that is believed to be a good case where this is likely, not surely, but likely due to dark matter subhalos rather than other more difficult to understand but less exciting effects. But yeah.
Okay, thank you.
Do we have more questions from participants? I think that we received a lot of information during this seminar, and the work is very interesting, and I wish you, Cecilia, success and strength in pursuing this large work. So, and I'm sure that we will join your collaboration. I'm interested in the chemical composition investigations, and already have done something in this direction. So it is
Great.
very interesting. So thank you very
Yes,
much.
many people are very interested in this stellar populations, and that's very hard. So reach out, and yes, we'll talk. Sorry, I interrupted.
Yes, of course. Many people are interested, and a lot of new discoveries will be done, I'm sure. So thank you very much, and I encourage participants of this seminar and other astronomers to share the news to the community, and see you again at our seminar.
Great, thank you.